Welcome back, everyone. This is the end of our second full week, right? I'm losing track of time. My landlord is mowing the lawn at the moment, so if you hear a lawnmower in the background, that's what that is. Not much I can do there. Um, so, project groups. I'm going to assign anyone who's not already picked a group by sometime today. So if you have a group and you haven't emailed me, do so very soon. Um, I've gotten, I think, 2 groups sent my way. Other than that, I'll post homework 4 tonight, hopefully before office hours. I'm moving my office hours from um, Saturday, from tomorrow to today, since we have a homework due tonight. Probably should have thought to do that days ago, but I didn't. So here we are. I think that's it for announcements. So let's talk about the content. Yesterday in the question and catch-up day, we talked about unbounded LPs and how they look in a Tableau, unbounded and multiple solutions. So if you're curious about that, go watch those, or go watch the first 30 or 40 minutes of that. And I mentioned, so the example problem we used did not have, its initial basis was not actually feasible to the problem. And I mentioned that this is a common issue, and so it has a couple of nice, clean ways to solve that problem. We're going to talk about those today. The book presents what is commonly known as the two-phase method, where we perform one simplex procedure on a sort of altered version of the LP, and then to find a feasible solution, and then we proceed back to our standard simplex algorithm from there. But first today we're going to talk about what's called the big M method, where we kind of conjoin both phases into one process. They're very similar, so we'll get to that. I guess let's go ahead and just jump in. So the big M method, and again, we're going to be doing example problems in 2 dimensions. And it might be easy for us to look at a problem in 2 dimensions and see and pick a feasible place to start our simplex algorithm. But a real world problem may have far too many variables, far too many constraints. It may be far too large in general to look at and find a feasible basis just off a hunch. We need some kind of systematic way to find these things. So the first method is the big M method. That's what it's called. This is similar. If you remember, we used a sort of a big M in our logic constraints back on lecture 3. So here is the same problem we looked at yesterday in the question and catch-up lecture. And we pointed out that in standard equality form, our initial basis, S1, S2, is actually infeasible because we get the solution S2 equals -6, which violates our non-negativity constraint. So this problem looks something like this on a plot. Yeah, I'll do it over here. So if we have a plot of these constraints, it looks something like this. This being our feasible region. So this basis with the slack variables, with just slack variables, corresponds to the origin, which we can see is not feasible. And we can pick that out from the tableau or from the LP systematically by noticing that we have a negative on the right-hand side of our standard equality form, or of our tableau, as we talked about yesterday. Yesterday, I pointed this out, and then I just pivoted straight to this point. Because I knew that that basis was feasible. But like I mentioned a second ago, we may not know that about our problem. We may not know which bases are feasible. So we need to change our problem up in order to fix that. I'm going to start by altering the constraints. This part follows what's in the book. x1 minus x2 plus s1 equals 1. This constraint is feasible, so we don't need to change it at all. This has a positive right-hand side, so there's nothing problematic there. The second constraint is infeasible. We're violating that constraint. So we need to change it somewhat. We're going to add what's called an auxiliary variable, A. Add auxiliary variable A to violated constraints. Or in this case, we're actually subtracting A. And I think actually, yeah, that's true in general. Subtract auxiliary variable A from the violated constraints. Remember that our constraints are only in standard equality form. In their, well, this is actually in the canonical form for this basis. Because we have plus plus 1 times all of our basic variables. So if you're in the canonical form, the constraint is only violated when there's a negative on the right-hand side. And to each of those constraints, we're going to add an auxiliary variable. or subtract an auxiliary variable. This is sort of like a slack variable, except that it takes it represents the negative of a slack variable. It's exactly the opposite in that it is still the distance to our constraint, but it's that distance to being feasible. Whereas the slack is the distance to being infeasible, A is the distance to being feasible, if that makes any sense. In a canonical form, they're always going to be negative. And then we need our non-negativity. Including for our new auxiliary variable. Now let me move this down here. And then we want to maximize. And unlike the two-phase method, which is presented in the book, the big M method preserves some of our original objective. And all we do is subtract some big M times A1. So the two things we've added are these. Then we subtract M times A from the objective. Where for some sufficiently large M. All that means is that M should be way, way bigger than any of the other coefficients in the objective. We just want to prioritize changing the auxiliary variable somehow. If you happen to have a minimization problem, you would actually add M times A. So what this does is it says A, since we're infeasible, A is positive, right? In this basis, A is positive, so we're penalizing having a positive A very heavily, which incentivizes the simplex algorithm to address A1 first before thinking about any of our other decision variables. It wants to get rid of the A1 term as best it can. And in maximization, we do that. We penalize that by subtracting. In a minimization, we penalize it by adding. Okay. So let's do an iteration of this. So this turns into the tableau. Maybe I can fit that all in there. Z, x1, x2, s1, s2, a1. To -1, 0, 0, -1, or correction, -m, but we are negating this. So why is that positive now? Right. Yeah. Of course. Yes. Okay. We'll continue. 1, -1, 1, 0, 0. 2, -1, 0, 1, -1. And this is still a -6. I missed that up here. It's a -6. And that's what a tableau looks like. Now, we're still noticing that we have this in feasibility, and that's because we have yet to put this in the correct basis. So we want to include all of our auxiliary variables in the basis. All of our slack variables that are infeasible, that are in the basis, so in this case it's just S2, we're going to get rid of that S2 and put in A1. So pivot to include all auxiliary variables, which means that we are pivoting on this entry because we want A1 in and S2 out. Notice that this row has its identity entry in S1 or S2, so we're pivoting out S2. We're going to do that by duplicating this. And we're going to start with row 2 prime equals row 2 times -1. Then we give us row, well, We have a 0 already in row 1, so row 1 doesn't need any alteration. Row 0, however, needs to be changed to this. So, oh, correction. I'm going to subtract m times row 2 prime. So m minus m, 0. 0 minus negative m is positive m. 0, so that's unchanged. 1 minus negative m, or 1 minus positive m, rather, is 1 minus m. Negative 2 minus m is negative 2 minus m. So now we have this matrix, this tableau. Let me crunch this in a little better. And we'll notice that none of our constraints are violated. So in sort of the traditional sense, this tableau is feasible. But we have an auxiliary variable in the basis, so it's not feasible to our original problem still. We're still at the origin, so we still have x1 and x2 equals 0, which is still not feasible to our original problem. To the original problem. But now we can perform simplex sort of like we typically do. So we want to pick the non-basic variable with the smallest negative value. And remember that m is positive, so S2 is out because m would be positive. 1 minus m. We're kind of assuming that m is a very, very big number, so it's likely that that's negative. But this number is definitely negative, and it's in fact more negative. So we're going to pivot on x1 for this exercise, and then we need our b over a. So that's 1 over 1. 6 over 2 is 3. So we're actually going to pick that entry, smallest positive, and pivot on that entry. So let me grab our new tableau, paste it in there, and in fact, whoop, I think I just inserted a new page. And we want to pivot to something else. we have a 1 in that row, so that row is not going to change. But I also neglected to change our right-hand side. So we need to change that. That should have been a minus m. And up here as well. Minus m. And also the objective row needs to change. So let's start with the objective row, I guess. R0 prime is R0 plus 2 plus m R1, which gives us 0 there. 2 plus m times negative 1 plus 1 minus m is 1 minus 2 minus m is negative 1 minus 2m. S1 is now plus 2 plus m. Yeah. S2 stays as m. A stays as 0. And the right-hand side, negative m plus 2 plus m is going to be 2. Row 2. Prime is row 2 minus twice row 1. 0, negative 1, nope. 3. Negative 2, negative 1, 1, 6 minus 2 is 4. So, we're still not there yet because A is still in the basis. So we're still not at a truly feasible point. So, still not feasible. So, we do another simplex iteration. That's our only negative entry. So we're going to pivot x2 in, get our b over a. We have a negative 1, so ignore that. And we have a 4 over 3. So we pick that one and we pivot on this 3. And I think I can fit this all on this page. we are going to have to change this row too. And here we should be pivoting out our A1. So if this goes as we are perhaps planning, we should be feasible after this iteration because we're pivoting out our auxiliary variable. Row 2 prime is 1/3 row 2. Row 1 prime is row 1 plus row 2 prime. One minus 2/3 is 1/3. Negative 1/3 and 1/3. 1 plus 4/3 is 7/3. Yeah. And then finally, row 0 prime is row 0 plus, or, yeah, plus a 1 plus 2m row 2 prime. Which should give us 0 there. Let's just verify that. Negative 1 minus 2m. Excuse me. Plus 1 plus 2m. The 1's cancel, the 2m's cancel. Yeah, that's 0. Good. I did that right. 2 plus m minus 2/3 1 plus 2m is our next one. Gross, so 2 minus 2/3 plus m times 1 minus 4/3 is 4/3. Yep. 2 is 6/3 minus 2 is 4/3. So minus 1 minus 4/3 is negative 1/3 m. So we're getting a little yucky here. This is the price we pay. Also, I'm blocking all of that math with my head. Then we have m, so that's one computation. This one is going to be 1/3 plus 2/3 m. S2 is negative 1/3. What do we think about this? Does this row actually matter? Yeah, it does. I'm going to do this in a different color so that we can differentiate these things later. S2 is m plus, correction, minus 1/3. 1 plus 2m is 1/3, negative 1/3 plus m times 1 minus 2/3 equals negative 1/3 plus 1/3 m. And that just barely fits. Right hand side is 2 plus 4/3 plus 8/3 m, which is 6 plus 4 is 10/3 plus 8/3 m. Gross. So now we have a feasible solution. It is the basis. Well, we have a feasible basis, right? x1, x2. Neither of those are auxiliary variables, and they take positive values, which means that this solution is feasible to the original LP. So let me see if I can write that somewhere. That's not going to get, here we go. When if the basis has no auxiliary variables and takes positive values, the basis is feasible. To the original LP. And that's what we have down here. And let me go back and find what we did yesterday to see if these tableaus match up properly. Okay, so here is the step we did yesterday. So I jumped immediately to the x1, x2 basis. And we had this tableau. which, as it turns out, I believe is the same as this. Yeah, so we knock out the A column and we erase all of the m's, set m to 0, and I think we have the same tableau. Let's go back. I think it looks the same to me. Good, that's how it's supposed to work. So I did my math, at least consistently between the 2 days. So let's grab this. So we want to, after finding a feasible basis or a basic solution, we remove the A column, remove aux variables, and set m to 0. Which is going to give us one too many things disappearing. So that is a negative 1/3 and that. Then we perform simplex as usual. Now, as we discovered yesterday, this problem is actually unbounded because we have two negative, well, this entire row, this is the only row that improves anything, or column that improves anything, but that entire column has a negative coefficient. So that tells us that that problem is unbounded. So that's the big M method, and it seems a little convoluted, but it's nice because it lets us use a single tableau the whole time. We don't have to swap tableaus partway through, like we're going to have to do for the two-phase method. Yeah. We do still need to get rid of our M, so we do still need to alter our tableau, but we don't need to sort of restart, if that makes any sense. So we have that. That's a good method. The other traditional method for this is called the two-phase method. That's the method that the book shows off. It's a little more robust because we don't use a big M. We don't use an arbitrarily large coefficient. But like I mentioned, we do have to sort of reset after finding a feasible basis. Not a huge deal, and any solver, publicly available solver you're going to pick up will already have these things built in, but it's important to know how your algorithm is working. For example, in my own research, we've been doing, me and my advisor have been doing redistricting, so creating maps of political districts in Virginia and other states. And we are using an integer program to do that, and that is an enormous, enormous problem. And the integer program takes a long time to solve, even on what would be considered unrealistically small problems. So finding an initial feasible solution is difficult because it's the same process as finding the optimal solution. So it could take as long or longer to find a feasible solution as it does to find the optimal given a feasible solution. So half of our time is eaten up trying to find feasible solutions. So the remedy for that is to give our solver a feasible solution to start from. It could be the solution that is actually in practice at the moment, or it could be something that was created by a heuristic. So it's important to understand that this is just as time-consuming as the regular simplex method, but that for small LPs, that time-consuming, or even any linear program without integer variables, that time consumption is actually not a big deal. It doesn't take very long, unless you have integer variables or nonlinear constraints or tens of other things. So let's get into the simplex, or the two-phase simplex method. We're going to start exactly the same. We have the standard equality form, canonical for S1, S2. We're going to introduce an auxiliary variable, and we're going to completely change the objective function. We actually don't even want to maximize, although you could write it as a maximization problem. I'm going to do a minimization. So we want to minimize A. That's it. That's the whole objective. If you had more than one auxiliary variable, you would sum up your A's. And remember that A is non-negative. So let's get ourselves another Tableau going. And remember, we're not using this objective, we're using this objective. And we're going to negate our objective. And our right-hand side, currently A is non-basic, right, because it has a -1 down here. So our right-hand side, our objective function is 0. And we have all of the rest of the things. Don't need a plus. Is this the same? Error, I think. Yeah. This should be a plus back here on the first page. Did I propagate that through this whole problem? I think I did. Then how did we get there correct? Huh. Oh, wait. Nope, I was right. That is negative because I've put this in, I've swapped the direction of this inequality by multiplying each side by a negative. So that is a negative. So we're good. Don't worry about that. Sorry if me jumping back and forth there was a little bit jarring. But I thought I spotted a problem. This should be a +1, -2, -1, 0, 1. So now we do simplex on this. We want to swap in A, and we get a B over A that is undefined, and 6. So whereas in the big M method, remember we had to artificially add our A. Oh, wait. Remember everyone. No, we're minimizing here. And we're going to get, I just got confused by this. So this is an important thing to point out. When you're minimizing, you want to pick when minimizing, pick the non-basic with largest positive objective coefficient. In the tableau. So that just tripped me up. because in fact we do need to pivot this manually to put A in the basis. So we want, again, our S1 and A. This is our target basis. So we pivot on this entry. I might not cover that up. Too bad. We start by negating all of that. So R2 prime is negative 1 times R1, R2. And row 0 prime is row 0 plus R2 prime. Row 1 doesn't change, but we do have yeah, plus row 2 prime, so that's 2. Writing too fast. 2, 1, 0, negative 1, 0, 6. So this is our new tableau. And now we perform simplex on this like normal. Of course, we are still minimizing, so we're going to pick the largest positive. So we're minimizing here. Minimize. Largest positive number. And then we take our B over A, 1 divided by 1, and 3. And again, we're going to pick the smallest one. That's how it goes. And so that's the same pivot we did before, remember. So I am just going to reach back in time and grab most of that tableau from before. But the difference is that our objective function row is going to be totally different because we have a different objective function. And we were pivoting on that entry. So row 0 prime is row 0 minus twice row 1. is 0. 1 plus 2 is 3. 0 minus 2 is negative 2. This is unchanged. This is unchanged. And that's a 4. So let's compare. Actually, I still have it copied here. Notice that our objective function row is completely different. So I'm going to demarcate this for us. Same step from the big M. Because the process was sort of the same. We did the same pivot out of the gate. That may not always be true. The pivots may not always line up between the two methods, and you may not end up with the same initial feasible solution. But if there is a feasible solution, if the LP is feasible, both of these methods should terminate in a feasible basis. So let's grab this one, paste it here. Again, we're minimizing. So we pick the largest positive, and we B over A, negative 1, ignore him, 4 over 3. We pivot around that entry. Again, that's the same pivot we did before. So I'm going to, again, reach back in time and grab the relevant tableau. So I don't have to do all that math again. So we tack this on, we say R0 prime is R0 minus R1. Not R1 prime, just R1, because we have the 3's lining up there. So x2, 0. Negative 2 minus negative 2 is 0. Negative 3, or negative 1 minus 1. Negative 1 is 0. 0 minus 1 is negative 1. Right-hand side, 4 minus 4 is 0. So again, we found the same basis and in fact the same solution. x1 is 7/3, x2 is 4/3, s1 and s2 are 0, and a1 is 0. Happy day. We got the same thing, slightly different process, a little less cumbersome, a little more robust. But now, remember at the end of the big M method, all we had to do was erase our M's and our A column, and we were good to go, ready for the next stage. It's not quite the case here. We have another step to go. I'm going to drag this up here, put that over here. So we need to do some work. Do some work before simplex can resume. Specifically, we need to doctor up the objective function somewhat. So here's what we're going to do. I'm going to grab him. Just like last time, we're going to erase a column. Don't need that variable anymore. It's taking up space. Then we're going to put in the original objective to the original problem. Demarcate that for us. So we're going to put in, what was the original objective? It was 2y? 2x1 minus x2. I don't need the variables in there, just the coefficients. And now it's not in canonical form anymore, right? Because our objective, our identity matrix has been broken up. So and then we need to recanonize put it back. In canonical form. For the basis we found. Am I covering that up? Scoot it. Can I sneak it in down here? I sure can. To do that, we want we want to put zeros here, right? So to do that, the easiest way is just row 0 prime is going to be row 0 minus 2 row 1 plus row 2 for us. For this problem, basically your basis in the A part of the tableau should already be in row reduced form. So we just need to subtract that row times the coefficient in the objective to cancel that out. So that's the general format. So we're going to end up with minus twice row 1. So that's negative 1/3, negative 2/3 plus row 2 is minus 2/3. So that's going to be minus 4/3. And then we're going to have plus 2/3 minus 1/3 is going to give us positive 1/3. And the right hand side is going to be 7/3, negative 7/3, or negative 14/3. Oh wait, what was in the... Yeah, it should have been a 0, I think. Is that true? So that's going to give us... Did I forget to negate this? I totally did. I forgot to negate the objective. So we actually plus and minus, which should just flip these signs, and then we have a positive 14/3 minus 4/3 is 10/3. So I figured that out because my right hand side entry was going to end up negative. So something was wrong there. Anyway, that should be the same basis or the same tableau we found at the end of the big M method. And we are just in time. That's 10:45. Sweet. So that's those two processes. Not quite identical, but they give, in this case, they give the same results. They may not always do that. Both are useful. So you guys are free to go because it's 10:45. I'm going to stick around for a little bit, though. You too, James. Have a good weekend, everyone.